So clearly, this x plus 5 is up to a certain amount of mischief. All that range of epsilon error around the 9 in the output, around the 9 we'd have gotten if we just had an x equals 4, has to come from the x plus 5. We saw that when we set the value of x minus 4 to less than 1, we ended up with a value of x which was between 3 and 5. Now, we can take that x is less than 5 and more than 3, and proceed from here by adding 5 to all parts to see what the range of y output is actually going to be. Eight is less than x plus 5, which is less than 10. So we see that the most that the x plus 5 can do with the way we've defined x is multiply the rest of the equation by 10. And now we have our candidate for delta. The absolute value of x minus 4 is less than delta, which is equal to the minimum 1 or epsilon over 10. And that's how they give this to you in a textbook with a minor flourish, and it's not very enlightening as it stands. In fact, we're really only interested in the epsilon over 10. Baffling, huh? This is where we need to recall that the delta and the epsilon are not the input, the x, and the output, the f at x, but the amount of divergence we can expect in the output when we diverge from a certain input. That's what we mean by the limit as x approaches 4 of x squared plus x minus 11 equals 9, and we rewrite this as the absolute value of x squared plus x minus 11 minus 9. This here represents the margin of error, the difference between what we want as output, the 9, and what we're going to get from the equation itself when we put in different x values. While this bit, the absolute value of x minus 4, means the difference we're allowing between the ideal input x and what we're actually using as an x value. Our overall goal is to show that we can control the output by controlling the input. You may wonder, why don't we just do that? Why not show by trial and error how much difference in input gives what difference in output? Try, say, 4.5, 4.1, 4.001, 3.9999, 3.01, 3.001, and so on. Well, first, because that wouldn't be a proof, we can always control the output within certain input parameters. It would just be many examples of our doing so, which in themselves only establish a likelihood that it would always work. A practical example might help us here to show us why we really want proof. Let's say we've got a bow and arrow and a target we're interested in reaching with a bullseye. And let's suppose also that we have an equation that allows us to account for the distance, gravity, wind, and other factors which might throw off our aim. And this equation is programmed into a telescopic sight, which is fixed onto the bow. We would like the display on our telescopic sight to tell us how far off center of the crosshairs the target can be and have us still be able to hit the center. A delta-epsilon equation that compared the delta input difference with the epsilon output error would allow us to be sure we can always hit the bullseye. And there are military and aerospace applications where trial and error aren't good enough. Can you take out that incoming missile? Can you rendezvous with that distant satellite? Here you need proof-sure certainty. Okay, back to our equation. X plus 5 absolute value times the absolute value of x minus 4. When the absolute value of x plus 4 is less than 1, the biggest epsilon error that, let's see, so if this is set at 2, less than 1, less than 1. The biggest epsilon error that the x plus 5 can produce is going to be nearly 10 units off. And we can cope with that greatest epsilon of nearly 10 if we make the delta less than 1/10. Then we have a delta that will undo any epsilon error that the rest of the equation introduces. If we add nearly 1 to our input, our delta definition tells us we need to reduce the total epsilon error of the output to 1/10 of whatever it was to control it perfectly. That is, to be sure the equation adds no more to the output than the less than 1 we're admitting as the definition of delta. So, if we're making this adjustment to the results of our input, we're saying essentially f at 4 plus 1/10, which is going to be equal to f at 4.1, which is equal to 9.91. And if we allow this this controlled difference in the delta input in the other direction, in the negative delta direction, then we get f at 4 minus something less than 1/10, which let's say would be something less than 4, f at 3.9, which would be equal to, which would give us an output equal to 8.11. And if we look back at our graph of the function, we'd see that, okay, when f is 4, the y is 9, and so 8.11 would say be here, 9.91 would be about here. They'd both be within 1 unit of the output, whereas the variation we got before, we had 19 up here and we had 1 down here. So basically, out of the entire possible range, with this delta definition, we're able to control the output so it always falls within the less than 1 divergence we worked into the delta definition, within that 1 of the target output of 9. We undid all the unwanted consequences of allowing delta to be something under 1. We define then the absolute value of x minus 4 is less than delta, which is equal to minimum of 1, or whichever is smaller, 1, or e over 10, to say that the delta has to be less than e over 10 to stay within our chosen error tolerance. But if there's some other fraction, some other less than 1, which is even smaller, that's fine too. Now, to return to our bow and arrow, this is like saying that so long as the target here's the crosshairs, and here's the target with its bullseye appearing in our crosshairs. So long as the target shows a less than 10% shift from dead center on the crosshairs, we can be sure we'll hit the center circle with its 1 unit radius. The 1 unit radius representing for us the variation in delta input of less than 1 that we just mentioned. Now we're at part 5 of the proof. Show how it's done. The foregoing was, with much editorializing, how we came up with our candidate for delta. That is epsilon over 10. This is the rapid fun part of the proof. Basically, we recap what we just did. Let's see, that would be x squared plus x minus 11 minus 9 is equal to, well, first we're going to simplify this. X squared plus x minus 20, and that's equal to the absolute value of this in factored form, absolute value of x plus 5 times the absolute value of x minus 4, which is equal to something less than 10 times x minus 4, which is going to be equal to 10 times absolute value of e over 10, which is obviously going to be equal to e. So we've shown that all of this, with the delta value that we've chosen, the absolute value of e over 10, gives us something which is less than e. Final part of the proof. 6th part, draw the conclusion. We have shown that the absolute value of x squared plus x minus 11 minus 9 is indeed less than epsilon whenever the absolute value of x minus 4 is greater than 0 and less than our delta, which we have chosen to be the whichever is smaller of something less than 1 or something less than epsilon over 10. And so the limit as x approaches 4 of x squared plus x minus 11 is indeed 9, which means that by controlling the x input to within any delta difference we like of the target input, here 4, we can be sure that the y output will be as close as we please to the ideal output, here 9. Since we have a quadratic equation which factors into two parts, we have to define and retain the value of one part to allow us to wholly control the other, which is why we still got the epsilon error tolerance of something under 1 in the output. But since the only divergence from the ideal output of 9 is what we permit as the delta, by defining delta as small as we wish, we can make the epsilon as small as we wish. So, no matter how close x gets to 4, y only gets closer to 9, in every case without exception. And that's the QED of it, what we set out to show.